Assalamualaikum and a very good evening. My name is Alfizatul Afifa binti Saudi, and my other fellow group member are Edric Bugina Awang, Sri Shabindran Anak Laki Subramaniam, Nur Syaris Mazwin binti Syaruddin, and also Nur Fakurazi bin Muhammad Azmi. We are from group 2. So our project are Bandpass filter circuit design using operational amplifier. For the introduction, the butterworth filter is an analog filter design that yields the best output response with no ripple in the passband or the stopband, resulting in a maximally flat filter response at the cost of a rather large transition band. Next, I would like to pass to Edric.
Okay, so today I'm going to explain my part and Fakurazi part, which is the methodology part. I'm going to explain about this part that we are making using the multism. We are choosing the butterworth pass for this to match the requirement of this project, and they are including the low pass and the high pass. For this part, we are using capacitor, and we are using the input-output, and also we are using some resistor, which is include in the high pass and the low pass. For the high pass, we understand the difference between this is low pass is it attenuates the high frequency, and the high pass filter it attenuates low frequency. We are also using raw input and output device, which is an audio filter for this project. When connecting the circuit with the wire, we managed to get output in the resulting discussion that we are going to explain a little bit more. Okay, we are choosing the magnitude and the phase graph. Okay, the capacitance is changed based on the value we want, and also the resistance we also change it to the value that we want, so that we altered it few times so that we can get the perfect output. We're also using the ground cable to drain away any unwanted build-up of the electric charge. Okay, moreover, we make the circuit in two phases, which is the top one and the bottom one, to show the difference between the high pass and the low pass in a clear way. We also want to save a smaller space, so that we using the circuit as two type of circuit. Okay, the multism circuit we are using is our own idea, and also we choose the audio filter for this project. So that's it for me.
Hi, my name is Nur Syaris Mazwin, and I will present about the result of our project. Shown in the poster is the result of the butterworth filter using multism software. The upper one shows the magnitude, while the lower one shows the phase. According to the internet, an ideal electrical filter should not only completely reject unwanted frequencies, but should also have uniform sensitivity for the wanted frequencies. Such an ideal filter cannot be achieved, but by using butterworth that increases the number of filter elements of the right value, successively closer approximation was obtained. The frequency response of the butterworth filter has no ripples in the passband and rolls off toward the zero in the stopband. Butterworth filters have a monotonically changing magnitude function with omega, unlike other filter types that have non-monotonic ripples in the passband or the stopband. Monotonically means that the signal does not progressively increase or decrease. As the order of the filter increases, the quick roll-off around the cut-off frequency also improves. Its phase delay is largely frequency dependent. The delay that was meant are the delay times experienced by a signal's various frequency components when the signal passes through a linear time invariant system. What was meant by frequency dependent is that different frequency components experience different delay. Next, I will pass this to my groupmate Sri Shavindra for the next part.
Good day, dear lecturer and fellow friends. I will continue the next part, which is discussion. Before we design a bandpass filter circuit, we had done calculation for low pass filter, which is to remove all high order frequencies up to 10.25 kHz from the input signal. In order to calculate capacitor value for the low pass filter side, we make use the formula, which is Ck equals to dk over m times 2 pi times ft, which is k is represented as order number, while ft is out of frequency, which is 10.25 kHz, and the m is the magnitude coefficient, which is 10 kHz, which is fixed number, and the dk is normalized capacitor value. In this case, we use fifth order high pass butterworth filter. So we will refer table normalized denominator polynomial in factor form, which is I already attached in the report. By using this table, fifth order polynomial 5 poles were obtained from which normalized capacitor value or decay value were calculated. Next, high pass filter is designed to attenuate frequency from 0 to the 9.75 kHz. Cut-off frequency is set to 9.75 kHz, and the standard capacitor value for audio circuit design chosen to be 0.01 microfarad. In order to calculate value high pass filter, we use formula RKM over dk, where m is the magnetic coefficient, which is 1720.594, while Lc is the 9.75 kHz. Cs is 0.01 microfarad, as I mentioned just now, while dk is the fifth order normalized capacitor value, which is referred to the table where I already attached in the report. By using this formula, we obtain that first capacitor is 3 nanofarad, while the second capacitor is 2 nanofarad. The third capacitor is 680 picofarad, while the fourth capacitor is 5 nanofarad. And the last one, fifth capacitor, is 417 picofarad. By using the formula where we use M over D1, we have obtained the resistor value, which is the first resistor value is 981.514 ohm, which is approximately 1 kHz. And using the same formula, we obtain the second resistor value, which is 1.2 kHz, and the third one is 3.9 kHz, and the fourth is 560 ohm, and the last one is 5.6 kilo ohm. So what we can say is, as I mentioned just now, the fifth order low pass butterworth filter is a type of filter that allow low frequency signals to pass through the while attenuate to reducing the amplitude of high frequency signals. The cut-off frequency for this filter, which is 10 kHz, meaning that frequency below 10 kHz will pass through with the minimum attenuation, while the frequency above 10 kHz will be greatly attenuated. The frequency response of the butterworth filter is known for being maximally flat in this passband, meaning that the frequency response does not vary greatly in the cut-off frequency of range. A fifth order high pass butterworth filter, on the other hand, it is opposite of a low pass filter. It allows high frequency signals to pass through while attenuating low frequency signals. The cut-off frequency for this filter is also 10 kHz, meaning that the frequency above 10 kHz will pass through with minimum attenuation, while the frequency below 10 kHz will be greatly attenuated. Like low pass filter, the frequency response of the Butterworth high pass filter is known for being maximally flat in the passband. In this case, this order refers to the number of poles in the filter. The more poles in the filter has, the steeper the roll of which will be in the frequency response, and the more attenuation the filter will have for frequency outside of the cut-off range. The order of a filter in this case is this order refers to the number of poles in the filter's transfer function. A pole in the filter's transfer function represents a frequency at which the filter's gain drops 1 over square. We can say as a maximum gain in decibel as -3 point. So in conclusion, what I can say is a fifth order filter will have a stepper roll of a greater level of attenuation than a lower order filter such as second order filter. Then this means that a fifth order filter will be able to reject unwanted frequency component more effectively than a second order filter. It also worth mentioning that Butterworth filter are known for having a maximally flat response in the passband, meaning that the frequency response does not vary greatly in the cut-off frequency range. This makes the Butterworth filter a good choice of application where constant gain in the passband is desired. That's all. Thank you.
As a conclusion, in this paper, we presented a bandpass filter design using a Butterworth filter. Our circuit is composed using fifth order, and in addition, both LPH and HPF are combined to form this bandpass filter. The software we used demonstrated how to build the 10 kHz filter by applying the Butterworth filter design. So that's all. Thank you.